Hello, students. Hope you are doing great. We will wait for 5 more minutes. We'll wait for 5 more minutes and uh, allow students into this call. Yeah, so it's already 3:05 now. I'll keep admitting the students who request to join, but we will start with the session now. So once again, welcome to this practice assignment week 3, corresponding to the lectures of week 3 for nanotech and in agriculture. And what we'll be doing here is I'll lay down some general set of instructions for all the participants. So during this whole problem solving session, please turn off your mic and switch off your video chat. So whatever interaction between you and me should be through the comment box, because this class will comprise of lots of students, and so the only effective communication we can clearly have without any clutter is through the chat box, right? So at all times, switch off your mic and turn off your video chat. And what we'll be doing in this session is solving a practice. So these will be some practice questions, not the exact question that you are answering in your assignment, but this is a kind of practice set of questions from the same module that you are going to face. So this is corresponding to the week 3 module lectures, and we will start the practice assignment. So in this whole 2-hour session, we will go through each question in detail. So there will be 10 questions, multiple choice, as the same format as you are encountering in your assignments. And we will keep this session interactive. We'll try to answer as many questions as we can. So I encourage all the students to participate. And there is a reason. Uh, yeah, students, I would like to repeat. Please turn off your video chat and switch off your mic. And any kind of interaction with me will be via through the comment box. So as I was saying, that this will be an interactive session where the students I'll ask the students to guess the correct answer or answer the questions, and then we'll move on to the explanation and why the correct answer is the correct answer, right? And let's hope to be it's a fruitful and interactive session, and I encourage all the students to interact with me directly through the chat box, right? Yeah, I'll keep admitting students who are requesting to join. Let me share my screen. So before that, to all the students who have joined, I hope you must have received uh, emails from NPTEL course Nanotech in Agriculture regarding the recordings of these sessions. YouTube link is provided in those in those emails. You can visit that YouTube link. It is in my YouTube channel. So I have all these sessions recorded, and these recorded sessions will be uploaded in the YouTube week-wise. So you can visit them anytime, and you can repeat, watch them, and to solve your doubts, to understand this course better. And there is a reason this practice session is scheduled a little later than the actual coming out of videos, because this practice session is kind of a revision of your earlier modules. I know not all the students would be able to keep up with the daily watching of lectures. So if you have some piled up lectures, please go and watch it. And this assignment solving problem practice session will help you recall and refresh your knowledge about the lectures. Okay, with that much of introduction, let's start. In the chat box, I am giving the YouTube link of my YouTube channel where the previous two recordings, practice session 1 and practice sessions 2, are given. You can all copy that or watch it, and you will also get the link via email. So to all the newcomers, please turn off your mic and video chat during this whole session, and we will communicate via the chat box. Let me share my screen without any further delay. So students, can you see the slides that I'm presenting? Can you see my slides changing? If yes, you can just answer yes in the chat box. Just let me know. I'll wait for some time. You can just type yes or no in the chat box. Is my slides visible and are they changing? And is my audio clear? Then we can begin. Yes, sir. Good. Good, good. Yeah, I got it. Nice. So again, this course that we are going to pursue, we are currently pursuing, is nanotechnology in agriculture. And today we'll solve practice assignment week 3, corresponding to week 3 lecture module. And course instructor is Professor Mainak Das from IIT Kanpur. And my name is Ashutosh Behra. I'm a PhD scholar, PMRF at IIT Kanpur. And I'll be the TA for this course. So the first question of our practice assignment. Yeah. So the first question is, which one of this is not a non-ionic surfactant? I'll repeat the question again. Which one of this is not a non-ionic surfactant? Option A, polyglycerol alkyl ethers. Option B, glucosyl dialkyl ethers. Option C, crown ethers, ester linked surfactants. Option D, quaternary ammonium salts. What would be the answer of this question? Students, just try to recall the basics and the logics of behind the lecture week 3, or you can just guess the answer. We will anyway move to the correct answer, and we'll analyze why is it the correct answer. So please try to answer. You can type your answer in the chat box. To all the students who have joined recently, please turn off your mic and video chat. Any communication with me will be via the chat box for smooth conduction of this session. So question 1, which one of this is not a non-ionic surfactant? You can type your answer in the chat box. Whatever option you think is the correct answer. I'll wait for a few minutes to collect some answers, and then we'll see what is the correct answer and the rationale behind the correct answer. Right? Let us all participate and try to at least answer. It's okay if your answer is wrong. Do not feel shy. Be confident in answer. Even if your answer is wrong, we will come to know what is the correct answer and the logic behind that. So that actual final exam you would not mess it up and your concepts will be clear on the lecture week 3. So what could be the answer? There are some answers, students answering. Gaurav, option D, Makesh D, Vishnu D, aluminium salts. So students, I encourage everyone to participate. Just guess the answer. Even if you do not know the correct logic, just guess the answer or based on your understanding, right? Okay, some options are, somebody answered option B, mostly D. So let's see what is the correct answer. Enough answers for now. So the correct answer is quaternary ammonium salts. Option D, which many of the students have correctly answered. Well done. So let us see what is a non-ionic surfactant, right? On our understanding of non-ionic surfactant, what is a surfactant? A surfactant is a chemical compound that decreases the surface tension or interfacial tension between two phases. Those phases can be two liquids, a liquid and a gas, liquid and a solid, or anything. So surfactant is a chemical compound or a molecule which will coat two phases, and in this in our context it's nanoparticles. So surfactants, we use surfactants in many processes of nanoparticle synthesis to coat our nanoparticles, which will reduce the surface tension of those nanoparticles. Correct? And these surfactants may function as emulsifiers, wetting agents, detergents, foaming agents, or dispersants. So surfactants are not something very complex. We encounter surfactants daily in our life. Detergents are a kind of surfactant. Emulsifiers for fat emulsification, right? Foaming agents, soaps are also a kind of surfactants or dispersants. Now I have a quick question to ask you guys offbeat. Which method do you think uh, surfactants is widely used in nanoparticle synthesis? There is a certain physical method of nanoparticle synthesis in which we use surfactants very routinely. So can you guys guess the answer? Can you guys recall? You can mention in the chat box, which is the physical synthesis process of nanoparticles where surfactants are used very commonly. Seems like students, did you get my question? I was asking, where do you think surfactants is readily used in a physical, so there is a physical method of nanoparticle synthesis in which surfactant is correctly used, like highly used. I think there is a correct answer among the chat box. Shweta is correct. High energy ball milling is the physical method of synthesis in which surfactants are readily used. John, you are also correct, but emulsification is a chemical method of uh, synthesis, right? So in high energy ball milling, inside the ball, the high energy ball, so there are rolling balls and surfactant is added so that the breakage of nanoparticles happen very smoothly, and while the bulk material is reduced into nanomaterial size, these surfactants and reduce the surface tension and avoid aggregation of the nanoparticle back in the high energy ball milling mill. So Shweta is definitely correct, and thank you. So as we were reading about surfactants, so this is an example of where surfactants are used. Emulsification of bile salts. So this is a method in which fat globules, so this happens biologically. Bile salt gets emulsified bile droplets by these surfactants. So these green molecules here act as surfactants, coat the bile salt, and inside this blue core is the fat globule. So this is how they form kind of coating over the particles and do not allow them to aggregate, right? And another example of surfactant action is detergent action. Like I told you, we encounter surfactants on a daily to day basis. So this is a process of cleansing action of soaps and detergent. So these molecules, these spring-like tail molecules and head blob-like head molecule, these are surfactants or soap molecule. This will conjugate together with the dirt and remove it from the fabric, forming a micelle kind of structure. So these are some examples of surfactants. Now what our question was, which of these is not a non-ionic surfactant, right? So what are the type of surfactants? So there are mainly categorized into three types. Non-ionic surfactants, which has non-ionic group, means mainly no charge groups, and ionic surfactants can be further divided into cationic and anionic. So if the head group of the surfactant is positive, then we have a cationic head or a cationic group, and this negative charge is anionic group, right? And this is the hydrophobic tail moiety. So these are the different classification of surfactants. Non-ionic surfactants, so this is the class of our interest, have covalently bonded oxygen containing hydrophilic groups which are bonded to long chain hydrophobic parent structures. So these are hydrophobic parent structures, these long hydrophobic group, and in the head region they have covalently bonded oxygen containing hydrophilic groups. So here can be some hydrophilic groups that makes this head part hydrophilic and this long chain fatty acid or carbonyl uh, organic part hydrophobic, right? Thus, these long chain fatty acids can consist of ether, esters, of course fatty acids, and bulky hydrophobic groups constitute the non-ionic surfactants. So if we look back at our question, out of these, polyglycerol alkyl ethers, glucosyl dialkyl ethers, crown ethers, ester linked surfactants have all these bulky hydrophobic groups. So these all fall under the category of non-ionic surfactants. So which one of them is not a non-ionic surfactant will be quaternary ammonium salts. And this is how quaternary ammonium salt looks like. So this is the formula for quaternary ammonium cation. Quaternary ammonium, if there will be four R groups attached to the nitrogen atom and in conjugation, but this is not a stable This is not a stable moiety in itself, so it exists in conjugation with anion. So this cancels out the positive charge. Generally, the valence of nitrogen is 3, but here in a quaternary structure, there are 4 R groups attached to the N nitrogen atom and an anion to balance the charge. So this is not a non-ionic surfactant. It's a cationic surfactant because there is positive charge on the quaternary ammonium cation, right? So this is a cationic surfactant, not a non-ionic surfactant. Clear? Is it clear, students? You can just type yes or no. So this is a general style of how we will deal with these questions. We'll go to the root and basics of what the options could be and then clear out what is the correct answer. So that all of your basics and understanding will be very strong. Is it clear, students? You can just type yes or no in the chat box. Then we'll move forward. I'll wait for a few minutes. Okay, great, great. Students are responding. It's good. So I'll request all the students again to repeat the instructions to turn off their mic and video chat. You can interact with me through the chat box. Don't worry, this section is going to be a good interactive session. And I encourage all the students to try to answer these practice questions. So these are not the direct questions that you have solved in your assignments, but it's from the same module. For week 3 we are solving today week three's practice problem. So this will like solidify your concepts of the week 3 lectures, right? Let's move on to the second question. So the second question, I'll read it out loud. Ionic surfactants are more dashed than non-ionic surfactants, and non-ionic surfactants get dissolved as electroneutral molecules. I'll read it again. Ionic surfactants are more dash than non-ionic surfactants, and non-ionic surfactants get dissolved as electroneutral molecules. The options are A, hydrophilic, B, hydrophobic, C, electroneutral, D, absorbable. Come on, try to think. You can mention your answer in the chat box. You can type the answer, or you can just type option A, B, C, D, whichever you think is the correct answer for this question. And I encourage all the participants at least to brainstorm the question and try to find out the answer. I know these are all not very difficult questions. You can pinpoint down the correct answer. Ionic surfactants are more dash than non-ionic surfactants, and non-ionic surfactants get dissolved as electroneutral molecules. So let's wait. I'll wait for a few minutes for some answers. Students, please try to answer. Aditi says hydrophilic. Gaurav, hydrophilic. Pujita says second option, hydrophobic. Okay. Natraj, hydrophobic. Vishwakarma, hydrophobic. John says hydrophilic. Anuradha, hydrophobic. Akhileshwar, B. Venkateshwar, B. Okay, so judging from the comment section, there are two school of thoughts. One group says it's hydrophilic, the other group says it's hydrophobic. Okay. Yeah, thank you. Nice participation. Let's see what is the correct answer. The correct answer is A, hydrophilic, right? So all the students who have answered A, you all are correct. And it's not hydrophobic, right? Let's see what how the answer is hydrophilic, right? So if you look at the previous first question, we discussed the general structure of a surfactant. So if struct the structural and functional unit of a surfactant looks like this. So if you divide this structure into a head region and a tail region, so the head region will be hydrophilic or water loving, right? the head region will be water loving of a surfactant, and not just any surfactant, it's our ionic surfactant, right? So the hydrophilic moiety here will be charged, so the head group will be charged, either is the cation or an anion, and this portion, this long zigzag tail, will be hydrophobic or water hating, because it's consisting of long chain carbon atoms, right? CH3, CH3, C2H5, or any kind of esters, ether, all these molecules we have studied. And here again, this is an example showing different kinds of detergent and an example, sorry, surfactants and their example. So this is a surfactant, soaps containing sodium stearate. So this exists at in solution. When we dissolve this surfactant, it will exist as, it will dissociate into the ions. So cation Na plus here, and this long chain carbon fatty acid or carbonyl atom will be negatively charged because of this COOH through which Na was attached, right? Similarly, this is an example of, this is sodium stearate is an example of anionic detergent, because upon dissociation the remnant molecule is negatively charged. Understood? So anionic detergent, upon dissolving in water, the remnant molecule, the Na plus, will go away, conjugate with water, because water is also a polar group, and water is existing in OH plus, OH minus and H plus ions, right? So OH minus ion will form a shell around Na plus, and these H plus ions will conjugate around these negative moieties, right? Similarly, a cationic detergent, upon dissociation, this is the cationic salt that we encountered in the first question, quaternary ammonium salt, positive charge. So upon dissociation in water, chlorine negative, so chloride ion will be shelled, will be surrounded by positively charged H plus ions, and OH group will surround this shell. So they will have their own conjugate ions made up of water molecules. Water will split into H plus and OH minus. So in a jar of water, not every molecule exists as H2O. Some molecules exist as H plus and OH minus, right? So these will conjugate with the surfactants. And in a non-ionic detergent, whereas there is no such charge moiety in the head group, right? So there will be no conjugation with the water molecule. So no H plus OH minus can surround this, because there is no charged molecule here. That's why an ionic detergent, may it be anionic or cationic, will be more soluble in water. That's what the question was. Ionic surfactants are more dash than non-ionic surfactants. Now, if a substance is more soluble in water, it's hydrophilic, it's water loving. While hydrophobic is a substance which will not dissolve in water, like oil. Oil will not dissolve in water, right? So that is the reason why any anionic or cationic detergent will easily be hydrophilic, while a non-ionic detergent will not be hydrophilic. Now, if we look at this complex structure of surfactant, so here previously we looked at a single structural unit of a surfactant. This is an example of a surfactant called micelle, the complex structure. And in micelle, this represents the structural unit. There is this hydrophilic head, plus 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 plus, and hydrophobic tail, and this is the counter ion. So here it shows a cationic surfactant, because the head group is positively charged, and this counter ion, so there exists always water molecules and some counter ions in this around this. So a counter ion is the ion that accompanies an ionic species in order to maintain electrical neutrality. Because this head group is positively charged or polar, there should be a counter ion which accompanies these to maintain electrical neutrality. So if you do not have counter ion, then this water can split into H plus and OH minus, and then surround this micelle here, and form the conjugation. So the answer to this question would be, ionic detergents are more hydrophilic, water loving, than non-ionic detergent, and non-ionic detergent exist as neutral species in solution. Is it clear to the students? Did it make the answer understandable? You can just type yes or no in the comment box, and we can move forward. Is it clear to the students? And for students who have just now rightly joined, I'll keep admitting other students who are requesting to join. Please turn off your mic and video chat. Any communication with me will be through the chat box, and this will be an interactive fun session. So try to participate more in order to gain more knowledge. So just now we solved question number 2, and is it clear to the students? Let me check the chat box. Okay, yes, yes, nice. Well, let's move on to our next question. The next question is about a process of nanoparticle synthesis. The sol gel method of NP preparation, NP here means nanoparticle, is a dashed process. The sol gel method of NP preparation is a dash process. Option A, top down. Option B, bottom up. Option C, nuclear reaction. Option D, displacement reaction. Come on. Students, I want you to answer this question. I'll encourage everyone to just participate in this discussion so that you benefit the most out of it. You can just type the answer in the chat box. What do you think is the correct answer? Sol gel method of nanoparticle preparation is a dashed process. Is it a top down process? Is it a bottom up process? Is it a nuclear reaction process or a displacement reaction process? I'll wait for a few more answers. Students are already answering. It's so good. Keep up the participation. And as you can see, this question is not very hard. If you have the basics clear of the types of nanoparticle synthesis, you can just classify this uh, into the correct answer, right? Okay, Sarah, there are so many answers now, and all these answers unanimously agree upon option B. So it has to be the correct answer, right? So the correct answer is option B, bottom up approach. So the Sol-Gel method of nanoparticle preparation is a bottom up process. It's quite funny because option C and D are totally out of the question, right? Sol-Gel method of nanoparticle preparation is not a nuclear reaction or a displacement reaction. Nuclear reaction happens inside nuclear reactors. Though we have something in similar in terminology to the nanoparticle synthesis, we have something called nucleation, but it's not the same as nuclear reaction. And displacement reaction, I don't know why is it there, but just to make your life easy, this is a bottom-up approach. Now let's have a detailed look. So this is a simplified cartoon representation of sol gel synthesis, and in sol gel synthesis we generally produce metal oxide nanoparticles, right? So first we have in this container we have metal precursors or solution such as silicon or any metal we silicon titanium dioxide or in here silicon, hydrolysis, solvolysis and condensation. So this says that hydrolysis reaction is performed to obtain a component of the sol gel synthesis known as sol gel synthesis. Sol is the colloidal suspension of solid particles in liquid. So in a liquid media, we have colloidal suspension of these metal precursor solution. This constitutes the sol particles. Then what is the next component? Gel. Gel is a polymer containing liquid. Gel is a liquid in which there is a polymer, tangled and all. So it gives a thick consistency. We must have all used hair gels and other silica gels for cushioning, right? So first what happens? These metal precursor solution undergoes hydrolysis and condensation to give this colloidal suspension of these metal ions, metal particles in certain solvent. Then we add further condensation. This on further condensation, these sol particles turn into gel-like particles. So all these nanoparticles or these metal precursors will start nucleation and form polymers. So now this liquid will have a polymer containing liquid called gel, right? Now what we have to do, we have to just evaporate or somehow remove this solvent material to isolate our nanoparticle. This is what is shown here. So there are some specific processes of drying, air drying and carbon dioxide drying, which will give certain different types of gels, whatever nanoparticles, aerogel or zerogel. So these are not of our focus, but the focus, the point of me showing you this diagram is the method of sol gel. What is the principle behind sol gel synthesis? So we have precursors. We first hydrolyze it and condense it to the sol form where it is colloidal suspension, then further condense it to the gel form, and then dry out the dry out the solvent to obtain the nanomaterial, right? So what does this method provide advantage of? This method provides several advantages over other synthesis routes, such as control over the texture, size and surface properties of the materials. So in this method, we can control all these qualities. We can control the texture, size of the nanomaterial, surface properties. So here you can see we can apply two different drying methods to obtain two very different nanomaterials, aerogel and zerogel. You can easily differentiate the surface properties. This is more densely packed, this is lightly packed, which makes aerogel very light, right? It is easy to implement, low cost, high quality and production of materials with large surface areas. So generally sol gel is a method used to make nanomaterials with large surface area like silicon dioxide or titanium dioxide. Okay, so that is all about sol gel, sorry. Now, what is bottom up and top down approach? Since you all have answered very correctly, so I think this concept is very clear for you. But still, for generalizing it once again. So in top down approach, we always start with the bulk material, and the bulk material is then broken down into the size of nanoparticles through whatever approaches. That there are many approaches such as laser ablation, sputtering electro explosion, mechanical milling and all this. While bottom up approach, so top down, the terminology itself says we come from the top to the down. So the down size is the nanomaterial and we start from the bulk material, right? And the bottom up approach, we start from the small material itself and then grow it into the nanoparticle. So in bottom up approach, we start at molecular atomic level and there is a process called nucleation and its growth. So nucleation is a process of nucleation is a point of star synthesis, point of start of accumulation or changing the property of the molecular level precursors into the desired nanomaterial, and then the nanomaterial is grown. So nucleation and its growth. So here we see there is our answer. Sol gel process is a bottom up approach, which you were all correct. There are other bottom up approaches: chemical vapor deposition, laser pyrolysis, green synthesis, right? So to sum it up, bottom up approaches describe that nanoparticle synthesis from precursor by nucleation and growth. So we are starting with a small precursor and then we nucleate it and it grows into our nanoparticle. And bottom up strategy mostly falls under the chemical method of nanoparticle synthesis. So if you look at in most chemical method of nanoparticle synthesis, we start with the precursor molecule, then go through the process of nucleation and growth. While mostly physical method of nanoparticle synthesis uses top-down approach, where we have bulk of our material, then we grind it or we etch it or scratch it or we heat it. We apply all forms of mechanical force, heat force, thermal energy and radiation energy to break down the bulk material into the smaller sizes. So our answer will be solve the process is a bottom-up approach, which you all have answered correctly. So is this explanation clear to the students? You can just mention in the chat box. I'll wait for some time. It's good to see that many students are participating, but I hope that others who are not participating will find it interesting and start answering questions, right? You do not need to shy out. You take courage in what you are doing. Even if your answer is wrong, effort is what matters, right? And we will go through the correct answer even if your answer is wrong. So is this clear to the students? You can just post it in the chat box. Yes, yes. Cool, cool, nice. Let's move on to the next question. So we are at question number 4. Question number 4. I'll read out the question for all of us. Physical vapor deposition, PVD, is a widely used technique for the dash and surface coatings. Physical vapor deposition is a widely used technique for the dash and surface coatings. Option A, fabrication of thin films. Option B, plasma cleaning. Option C, surface etching. Option D, chemical etching. Students, try to think of your answers. You can even put a wild hunch. Type your answers in the chat box. I'll wait for a minute. Once we have enough answers, we'll see whether uh, our friends are correct about this. Physical vapor deposition is a widely used technique for which of the following functionalities? Dash. Physical vapor deposition is a widely used technique for the dash and surface coating. Fabrication of thin films, plasma cleaning, surface etching, chemical etching. I'll wait for a few minutes. There are still people joining. So the students who have joined recently, please communicate with me only through the chat box and turn off your video chat and mics. So the question we are encountering here is number 4, and you can just guess the answer. There are already oh nice, there are already many answers, and all of them unanimously say option A, which is the correct answer. So you guys are all right. PVD is a widely used technique for fabrication of thin films. Is the most important uh, uh, app, the most important use for which PVD is very popular. So fabrication of thin films. Let's move on to the detail. Thin film deposition is the process of creating and depositing thin film coatings onto a substrate material. Right? So what is a thin film? Thin film does not exist on itself. It's not a paper thin material. It's thinner than paper. And that's why thin film coating can only be done onto a substrate material. So we must have a bulk substrate onto which thin film coating can be done. These coatings can be made up of many different nanomaterials, from metals to oxides to compounds. So there are many different examples of thin films in which uses metals, oxides, and many other compounds. So one basic example of thin film is a transistor or a diode in which we have p-n junctions. So people who are not aware of p-n junctions or p-n junctions are, P stands for, p and n junctions are these transistor are present in electron acceptor and electron donor kind of materials, which are coated onto different substrate levels so that their electrical properties can be taken advantage of. So in p-n junction diodes and transistor, we have thin film deposition of these metals, mostly from the group, the one I had of the group carbon. So group 5 compounds, group 5 metals, sorry. Thin film coatings also may have many different characteristics which are leveraged to alter or improve some element of the substrate performance. So these thin film coating, besides being so thin, although they are very thin, but they can impart different characteristics to the substrate itself. So the substrate performance can be increased by thin film coating. If you look at the size scale of thin film coating, so 1 millimeter is the size of a sheet or a plate, acrylic board or a brass board or a sheet of paper, not of paper, few sheets of paper. Thick film comes under the range of 100 micromolar micrometers to what is this 1 micrometer or 1 by 10 power 3 millimeter. This is a thick film. Gold and aluminium foils, which are very thin, right? We think these are very thin. So these fall in the range of 10 micrometers to zero point 0.1 micrometers, 1000 angstrom. And thin film then comes in the range of 10 angstrom or 1 nanometers. 10 angstrom is 1 nanometer. 10 angstrom to 10,000 1000 angstrom. So 1 nanometer to 100 nanometer thin is a thin film. And lower than this scale is the atom. So thin film is almost close to one atom, one or few atoms thick. Now what happens in a physical vapor deposition method? So this is a setup of physical vapor deposition. Sputtering PVD. There are many kinds of PVD. Physical vapor deposition is a common technique to deposit metals. So in sputtering PVD, what happens? So there are two, here we see black, green. This is the sputtering target. Sputtering target means this is the material which we want to coat, or this is the nanomaterial or whatever. We want this as a coating on our substrate. So orange colored substance is a substrate. This will have a thin layer film of this green material. Now how do we make it so thin? We provide this sputtering gas. So here we have a gas. This gas here, inert atmosphere, this gas is argon. This gas will go at high speed and bombard this sputtering target. So this yellow arrow will go like this, bombard this sputtering target. Now when this gas bombards this sputtering target, sputter target atoms will be generated. So there will be this material will be scraped or whatever, the energy will be transferred physically, and then this will turn into vapor. So the solid phase will turn into vapor phase. And here in the inert atmosphere in presence of argon, this will form a plasma kind of substance. So we'll have vapors of metal or metal oxide in an inert atmosphere, and then from this plasma kind of state, these nanoparticles, these target atoms, will then escape the plasma state and deposit on the substrate as a thin film. And here there is a voltage difference to attract these charged or these atoms or the plasma state atoms, right? So we have a sputtering gas which will bombard the sputtering target. There will be some nanoparticles or atoms escaping in the plasma state. Then these will also again escape the plasma state and deposit on the substrate as a thin film. So this is the process mechanism of a sputtering PVD. Now to show you another method of PVD and a comparison with the sputtering method of PVD. So here is an illustration of evaporation method in which this TFT substrate is a substrate and this green thing is the nanomaterial which we want to thin film over this substrate. So in evaporation method, we use electron beam for bombardment or heat. So we use both these methods. We heat this uh, target material, which will, and our sole purpose is to create this plasma kind of state in which the vaporized metal or material will be present in a inert chamber, or will be present in a state where it can deposit in the nanomaterial form as a thin film over the TFT substrate. While in sputtering method, we have argon gas, the sputtering gas, which will bombard into the material and then eject nanoparticles. Here we are using heat and electron beam. And there are commonly many other methods used for PVD, physical vapor deposition. Sputtering is one of them we have seen. Evaporation, electron beam evaporation. If you use electron beam to evaporate the vapor phase material, laser deposition. If you use the laser in pulses, which will provide the energy at certain intervals in some packets, known as pulse laser deposition, that will also cause the vapor evaporation and vacuum arc. So these are all commonly used PVD methods. So our question was PVD is used for dash kind of substance. So as you all have answered correctly, it's thin film deposition. We saw what is a thin film, what is the size range, and what are the different some important methods of physical vapor deposition. Is it clear to the students? If it's clear, you can just type, let me know in the chat box. You can type yes or no. Is the explanation clear to the students? I'll wait for a few answers. Great, great. I received your response. Okay, good that students are participating. Let's move on further to the fifth question, which is also on PVD. I'll read out the question. Physical vapor deposition (PVD) is a vaporization coating technique that involves the transfer of material at the dash level. This is a tricky question. Physical vapor deposition is a vaporization coating technique that involves the transfer of material at the dashed level. Option A, organic. Option B, atomic. Option C, liquid. Option D, plasma. PVD is a vaporization coating that involves transfer of material at which level? Basically, is it at the organic level, at the atomic level, liquid level, or plasma level? People, please, students, please write your answers in the chat box. Let me know what do you think is the correct answer. And students who haven't yet participated, please try to participate. Do not shy out. Have confidence. Even if your answer is wrong, we will see what is the right answer and we'll go behind the reason why the right answer is the right answer, right? I'll wait for a minute and check from responses. Please try to answer. And let's make this session more interactive. So this practice assignment is designed in such a way to brush up your knowledge and topics so that it's a kind of revision. So every session, if you attend it faithfully, it's kind of a revision of what you had already encountered in the previous weeks. So currently week 5 lectures are out and we are solving practice assignment week 3, right? Let's check. Okay, there are some answers. Aditi says B, Ganeshan says plasma, then Pradeep B, Gaurav atomic, Lal Charan B, Magesh B, atomic. Okay, so unanimously people have voted for atomic. Some answers also go to plasma, right? Let's see what is the correct answer. So the correct answer is atomic. It's not plasma. So let me take you back a few slides. The earlier slide we discussed that PVD. Just try to understand with me. PVD is used for thin film deposition, right? So PVD thin film forms falls in the range of atoms. That's what we discussed, right? Because it's ranging thin film ranges from 10 angstrom to 1000 angstrom. So it's at the atomic level. It's one atom, which is not ideally, it's one to few atom thick, just few atoms thick, thin film. The answer would not be plasma because in the PVD deposition method, plasma is an intermediate state through which these deposition happens. Plasma is not the answer because plasma is not getting deposited on the substrate, right? It's the atoms that are getting deposited on the substrate, atoms of the target material which we want to coat the substrate with. It's not the plasma. So the plasma is a straight state through which these atoms vaporize and then pass on and condense over the substrate to form a thin layer, right? Now let's see what explanation we have. So again, to define, plasma is one of our four fundamental states. So we have solid, liquid, gas, and the fourth fundamental state is plasma, which is characterized with the presence of a significant portion of charged particles in any combination of ions or electrons. So we have some charged particles, and we have and along with those charged particles we have a combination of other ions or electrons. That is plasma. So if we go back and see here in PVD deposition technique, we are already providing a voltage difference between the substrate plate and the target plate, or from where we are going to excite our molecules to form nanoparticles, right? There is already a voltage difference. So this will create charged plasma. That's what I was referring to here in the definition. Significant portion of charged particles in any combination of ions or electrons. And the nanomaterial that we form is at atomic level. So atomic level nanomaterial escapes the plasma and deposits on the target film substrate. So this is what happens in PVD actually. So the nanomaterial that escapes the plasma is atomic level, which is then deposited on the target film. So if we clear out any residual confusion, so this is the target film. This is the sputtering method of PVD deposition. Sorry, physical vapor deposition. So we have sputtering gas here, argon, which will hit the target. This is already at a voltage difference, right? Here we have plus and here we have earthing. And this state here, intermediate, is plasma, where the target nanoparticles will come and in presence of argon gas and other charged molecules will form the plasma. And then these atoms, atomic level nanometer, will escape and then deposit on the substrate, which will now form, right? So this is what is happening in a PVD. So this is the principle of PVD. So PVD is a technique to deposit atomic level nanomaterial. Okay, so is it clear to the students? Please let me know in the chat. Is it clear to the students? So the answer to this question would be atomic level nanomaterial. Question was physical deposition is a vaporization coating technique that involves transfer of material at dash level. So it will be atomic level. Yeah. Okay. Nice. Cool. Cool. Yes. Let's move on to the sixth question. Okay, so this is a big question here. You take your time and read this. I'll read it out for you. Read the following statements carefully and state, sorry, which one of this is not true for physical vapor deposition. So it's in continuation with the PVD technique. Read the following statements carefully and state which one of this is not true for physical deposition. The procedure for physical vapor deposition is as follows: sputtering evaporation of different components to produce a vapor phase. And B is supersaturation of the vapor phase in an inert atmosphere to promote condensation of metal nanoparticle. And statement C is consolidation of nanocomposite by thermal treatment under inert atmosphere. Now the options are: option A, statement C is not true; option B, statement B is not true; option C, all A, B, C are true; and option D, only A and C are true. So you need to verify all these statements, which of them is true, which one of them is false, and then decide on your answer. So it's a big question. You can, if you have already, I hope my slides are visible, and if you are already reading the question, you can type your answer in the chat box. And all students, please participate. It's a very fun interactive session. I hope so. And you get to learn only when you participate. So please try to answer which one of these options, A, B, C, D. It's about physical vapor deposition. I'll read the question again. Read the following statements carefully and state which one of this is not true for physical vapor deposition. The procedure for physical vapor deposition is as follows. Sputtering evaporation of different components to produce a vapor phase, supersaturation of the vapor phase in an inert atmosphere to promote condensation of metal nanoparticle, consolidation of nanocomposite by thermal treatment under inert atmosphere. So let us see if students have answered. Okay, there are some answers. Let's wait for some more time. This is a big question. I'll wait for 1 minute, and students, please try to answer. Even if your answer is wrong, you do not worry. You can just put in your efforts. Try to analyze the question. There are a few statements, and the question is asking which one of them is not true. There are a few answers. Some students say it's option statement B is not true. Option B. Some others say statement C is not true. Means option A. Let's see what is the correct answer. The correct answer is neither A nor B. Correct answer is C. All of them are true. A, B, C, all of them are true. Let's see why. Let's analyze the question here and then and here itself, right? Sputtering and evaporation of different components to produce a vapor phase. This is the first step, right? You either do sputtering with argon gas or any inert gas, hit the bombard the target or excite the target with evaporation techniques, heat or electron beam to produce a vapor phase. Vapor phase is the plasma phase. Supersaturation of vapor phase is in an inert atmosphere to promote condensation of metal nanoparticle. This is also true because in the plasma state, when will the atoms escape the plasma state? When the plasma state is supersaturated. Means in the middle, if we let me go back. Let me wait. Where it was? Yes, here. If you focus in this slide, so in this plasma state, what does this plasma state constitute of? Target nanoparticles, metal which is being targeted. This will occupy this space, and there are some other charged molecules in an inert atmosphere. So only when this plasma state is saturated, the atoms, the nanoparticle will escape the plasma state and deposit on the substrate. So statement B is also true. Supersaturation, the statement B says supersaturation of the vapor phase or the plasma phase in an inert atmosphere in presence of argon gas, or of course it's an inert atmosphere, to promote the condensation of metal nanoparticle. So in the end, what we are doing, we are condensing the metal nanoparticle, right? We are condensing the atoms of metal nanoparticle to deposit on the substrate as a thin film. So statement B is also true. Now statement C, consolidation of nanocomposite by thermal treatment under inert atmosphere. This is also true. So by thermal treatment here, it means the evaporation method of physical vapor deposition. Thermal energy is also a part of physical mode of synthesis. Consolidation of nanocomposite. So here it's a little bit tricky statement. Here it's saying in consolidation of nanocomposite. So if you try to analyze in the physical vapor deposition technique, so what we are doing is we are putting a thin film on a substrate. Now if we change the substrate as another nanomaterial, let's say whatever the substrate is a silicon dioxide nanomaterial, okay, and the physical vapor deposition what we are doing is for graphene. Let's say graphene is also a nanomaterial, graphene based nanomaterial. Then at the end of the day, when we in the chamber, what we are having is a nanocomposite. Nanocomposite is a material which has properties of many nanoparticles, or it's a conjugation between two or more nanoparticles which imparts different properties to the composite. So it's called a nanocomposite. So if we change the substrate to another nanomaterial, then can we not manufacture a nanocomposite by PVD? Yes, we surely can. And it can be by evaporation method by thermal treatment where we use heat. So if you remember this diagram here, so we use heat for this substrate deposition. So instead of this substrate, if we add another nanomaterial and we deposit another nanomaterial on the surface of the previous nanomaterial, then it will be a nanocomposite, right? So option C is also correct. So the answer to this will be statement A, B, C are all true. None of them is wrong. So let's revise again. Physical vapor deposition involves important steps. Now, what are the important steps? It has to occur in vacuum in an inert atmosphere. So the chamber in which this physical vapor deposition is carried out should be in vacuum and in an inert atmosphere. The first step is vaporization of material from a solid surface, which was the statement A. What we do is vaporize the metal or material from the solid surface and form the gas phase. Transportation of vaporized material. So this transportation of vaporized material is conducted through the plasma. When the plasma collects all this material from the solid surface, vaporized material, plasma will saturate and then transport the vaporized material onto the substrate. The material will move through the plasma and then deposit as a thin film on the substrate. And the final step is thin film generation by nucleation and growth, which is common for every bottom up nanomaterial synthesis. We need nucleation and we need growth. And now for vaporization of material from solid surface, we have many types of physical vapor deposition. We have sputtering, we have evaporation technique, electron beam evaporation or heat evaporation. We have vacuum arc. So these are some of the techniques for physical vapor deposition, vaporization of material from solid surface. For transportation of vaporized material, we have the plasma state. And then for thin film generation by nucleation and growth, we have the atomic level deposition. So due to nucleation and growth, we have atomic level deposition of thin film on the substrate. So if you analyze the components, so there should be vacuum. This is the substrate. We have a vapor phase going on, and this is the source from which we will generate the vapor. And if this blue material is a nanomaterial, then we will form a nanocomposite. If this blue material is some other regular substrate, we will just form a thin film over the substrate. So it depends on our material of choice, what we want to synthesize. So the answer to this previous question will be all the statements are true. Consolidation of nanocomposite by thermal treatment is also true. Supersaturation of vapor phase in an inert atmosphere is true, and sputtering evaporation to produce a vapor phase is also true. Do you agree with me? Is it clear, students? Because I want everyone to be clear about all these concepts.
so that your basics and foundation are very strong. Is it clear to the students? Do you agree with me? Yeah, yeah, nice. So we have some responses. Yes, good, good. So I want students to interact more and try to answer because we are already halfway through our session and we have completed. Which question was this? I think number 6. So we have completed sixth question. There are four more questions to go and we'll try to finish by 5. If we finish earlier, then I can take some of your doubts. You can ask me wherever you have not understood. I can repeat. That's why I keep asking after every explanation if it is clear to you guys, right? Let's move on to the seventh question. Seventh question reads, buckyballs are also known as A. Fullerene, B. C60, C. C70, and D. All of the above. So pretty short question from in comparison to what we have encountered in the sixth one. This is pretty direct question if you, and I hope student can answer. Buckyballs. I hope you have come across this term somewhere or the other. Buckyballs are also known as fullerene, C60, C70, or all of the above. I'll wait for a minute and for students to respond. Please try to respond at the maximum and try to participate. It just takes a few seconds to think about this question and just type the answer in the comment box. You do not have to turn on your mic or video chat. Do not have to be paranoid about that, right? You can just answer the question in the comment box, whatever you think is the correct answer. I'll wait for a minute for everybody to answer. Okay, so there are already some answers. Mansa says D, Gaurav all of the above, Rashmi D, John says C60. Okay. Sinta Pradeep says B, Dhanush Kumar D, Magesh says A, Reddy says B. Okay. So there are a lot of dispersed answers here. Buckyballs, I think most of us here know the answer. There are some more answers now. Good, good. Keep answering. Let's see, meanwhile, what is the correct answer? The correct answer would be D, as most of us have correctly answered and guessed. The answer is all of the above. Buckyballs are also known as fullerene, C60 and C70, all of them. So let's see where the confusion lies and what is the rationale behind this answer. Buckyballs are also called fullerenes. That finishes our option A, which were one of the first nanoparticles discovered. So buckyballs are the first, one of the first nanoparticles to be discovered. This discovery happened in 1985 by a trio of researchers working out at Rice University. Richard Smalley, Harry Kroto, and Robert Curl. So these are the scientists who discovered buckyballs at Rice University. These are also called as fullerenes. And what are they composed of? So buckyball is a carbon-based nanoparticle. So if you remember the first few lectures where we had classification of nanoparticles,
We had organic based nanoparticles, inorganic based nanoparticles, and carbon based nanoparticles. So buckyball is one of the carbon based nanoparticles. Buckyballs are composed of carbon atoms linked to three other carbon atoms by covalent bonds. However, the carbon atoms are connected in the same pattern of hexagons and pentagons you find on a soccer ball, giving a buckyball the spherical structure as shown in the following figure. So this is the figure that this point refers to. This looks pretty much like a soccer ball or a football. So all these vertices of the football of the hexagon and the pentagons are constituted by carbon atoms, and these sticks are covalent bond. This is a carbon atom. The center of the football is a hexagon. So these faces are hexagon, while there are some pentagons also. And carbon atom is peculiarly arranged like this, and this forms a nanomaterial. The most That's why, because this fullerene has an appearance of football, that's where it got its nickname as buckyballs. The most common buckyball contains 60 carbon atoms and is sometimes called C60. So C60 answers our second option. Second option was C60. C60 is a form of buckyball. So buckyball is a broad group of structures called fullerenes, and C60 is one of those structures, most common form. So it's understandable if somebody confuses C60 with buckyball, because C60 is a subset of a buckyball. C60 is also the common, that's why you keep hearing it. Other sizes of buckyballs range from those containing 20 carbon atoms to those containing more than 100 carbon atoms. So the size of buckyballs differs from 20 carbon atoms, the minimum, and there also exist bigger ones, more than 100 carbon atoms. And here is a structure of C60 and C70. So here C70, so C70, the suffix here suggests there are 70 carbon atoms arranged in this soccer ball like conformation, and this is also one type of a fullerene or a buckyball. So fullerenes are also buckyballs are also fullerene. C60 is also a buckyball. C70 is also a buckyball. The difference between C60 and C70 is C60 contains 60 carbon atoms while C70 contains 70 carbon atoms, and both come under the category of fullerenes as an allotrope of carbon. So the answer to this question would be all of the above. Buckyball are fullerenes. Buckyball is C60 as well as C70. Is it clear to the students? Do you agree with me? Just let me know. Type it in the comment box. Okay, great, great. Okay, let's move on to the next question. Question 8. Okay, so this is one of the other bigger questions, statement wise. Read the following statements carefully and state which one of them is not true for physical vapor deposition. Oh, I think there is an error here. Read the following statements carefully and state which one of the following is not true for biological synthesis. So there is a typo here. So this will be biological synthesis. Let me just rectify it. Meanwhile, you can read the question. You can read the question and try to answer. Yeah, so I'll read out the question again. Read the following statements carefully and state which one of the which one of this is not true for biological nanoparticle synthesis. The biological approach, which includes different types of microorganisms, has been used to synthesize different metallic nanoparticles, which has advantages over other chemical methods, as this is dashed greener, energy saving, cost effective. And the options are option A, statement C is not true, statement B is not true, and option C is all of them are true, A, B, C. Option D, only A and C are not true. Please read the question carefully. Sorry for the typo. The question is about biological nanoparticle synthesis. And try to answer, post your answer in the chat box. Come on, students, we are almost reaching to the end of this session. 2 to 3 more questions and we'll be done. So please try to participate if you haven't gotten a chance to really answer the previous questions. Which one of these will do you think is the answer? I'll wait for a minute for all the answers to pour in and then we can discuss. There are already some 3 4 answers. Which of these is not true for biological nanoparticle synthesis? Yeah, seems like we'll go on with 4 answers. So 4 of them have answered C. Statement both A, B, all of them are true. A, B, C. So biological approach for metallic nanoparticle synthesis is greener, energy saving, cost effective. Let's see what's the answer. You're absolutely correct. It's option C. So biological nanoparticle method synthesis is the most recent and newest form which is looking towards a greener future and is also energy saving, more closer to the natural methods, and very cost effective also because we have already biological moieties doing it on a regular basis. We just have to employ them in a correct workflow and a design to synthesize the desired biomaterial, nanomaterial. Sorry. Yeah. So if you see, what is the biological nanoparticle synthesis method? Nanoparticles are biosynthesized. Let me just yeah. Nanoparticles are biosynthesized when the microorganisms grab target ions from their environment and then turn the metal ions into element metal through enzymes generated by the cell activity. So the most important component of biological synthesis of nanomaterial method are enzymes present in the biological entities. So what happens is microorganisms will grab all these target ions, metal ions surrounding themselves, then with the help of enzyme convert them into metal and then deposit these metals. So that will be a process way of synthesizing nanoparticle naturally. Biological nanoparticle synthesis can be classified into intracellular and extracellular synthesis according to the location where nanoparticles are formed. So depending upon whether the nanoparticles are formed outside of the cell or inside of the cell, biological nanoparticle synthesis can be classified into intracellular and extracellular. The intracellular method consists of transporting ions into the microbial cell to form nanoparticles in the presence of enzyme. So this is a schematic
Just follow my pointer. This is a schematic for intracellular nanoparticle synthesis, in which these metal ions are transported inside the microbial cell, which is then deposited into metals in the presence of enzyme. Here it shows AuCl4 minus in aqueous medium, gold chloride, tetrachloride. Electrostatic interactions will take it inside the cell. This is a lipid bilayer. And then there are enzymes which will reduce the gold ions in the gold chloride, and then deposit it as nanoparticle, gold nanoparticle. Okay. So here this shows a reducing enzyme. This one is a reducing enzyme, gold nanoparticle, and conjugated to the water molecule. These green molecules are water molecules. There are some nitrates and other elements here, along with gold chloride and water molecules. This will come inside the cell, and the enzymatic reduction will happen inside the cell. That's why it's called intracellular. The extracellular synthesis of nanoparticles involve trapping the metal ions on the surface of the cells and reducing ions in the presence of enzyme. So at extracellular level, the protein will not be at the inside of the cell. Protein will be on the membrane, and whatever trapping will happen outside of the membrane. So here if you see, this is a silver nanoparticle getting formed from AgNO3 solution. So we have Ag plus ions and NO3 minus ions. Ag plus ions will be then anchored to the protein reducing enzyme, which will then convert this into the silver nanoparticle. And then this silver nanoparticle will be capped by a protein, protein capped silver nanoparticles, and then we can capping agent will then prevent it from aggregation. So this is a method of extracellular biological nanoparticle synthesis. This is a method of intracellular biological method of nanoparticle synthesis. And the new terminology which describes biological method of nanoparticle synthesis called green synthesis. Green synthesis, biological component itself act as reducing and capping agent. So the everything is biological. There is no, uh, there is nothing not natural. Everything is biological. It itself act as a reducing agent and a capping agent. Therefore, reduction of the overall cost of synthesis process. Thus, what happens? The cost is getting reduced because everything is naturally available. You just have to make it react in the appropriate conditions, and it's ready. So this last statement, option C, was cost effective. So cost is reduced because reducing agent, capping agent, everything is biologically available. External experimental conditions like high energy, high pressure are not required. Leads to energy saving process because unlike physical vapor deposition or ball milling, high energy ball milling, we require heat, thermal energy, and everything. And in chemical method synthesis also we require emulsifying agents, we require salt, gel, all these are, and polyol synthesis. So these are all required starting material. We require certain conditions, drying process, dehydration process. So nothing is required in green synthesis method. High energy, high pressure are not required. So energy is also saved. So it's a greener method. Can be used at large scale production of nanoparticles. Since a microbe can itself undergo green synthesis, so not many big infrastructure apparatus, inert atmosphere, substrate deposition, voltage difference, nothing is required. Everything can happen inside a single microbe, which can be grown in millions and millions of number in a petri dish or a conical flask, right? So this, if scaled up to proper volumes, can be produced at large scale. Nanoparticles can be produced at large scales, and is also eco-friendly as toxic chemicals are not used. Since there is no toxic chemical used, it's the most eco-friendly approach. That's why the name green synthesis. Thus, summarizing, the biosynthesis of nanoparticles has been proposed as a cost-effective, environmental-friendly alternative to chemical and physical methods. Green synthesis is ideally synthesizing nanoparticles that are formed at ambient temperatures, neutral pH, low cost, and environmentally friendly fashion. So there is no need of high temperature. Nanoparticles can be formed at ambient temperature, neutral pH, no need of any stringent conditions. It's very low cost and environment friendly also because there is no use of harmful chemicals. So the answer to our question will be biological method of nanoparticle synthesis is greener, is cost friendly, and the last statement was and energy saving, right? Is it clear to the students? Do you agree with me? You can just type yes or no in the chat box. We'll then further move ahead. Is it clear to the students? Why biological? Anyways, you all have had answered this question correctly. So biological process of nanomaterial synthesis is the future of nanoparticle synthesis. More and more ideas are developing in this sector, and it also has a big relevance to this course since we are going to see how nanotechnology can be used in agriculture, right? So if you have lesser chemical usage, we can have larger production and eco-friendlier systems, then it will be obviously beneficial for agriculture and crop plants. So students, just tell me if it's clear or not. Yes, yes, okay, great. Let's move on to the next question. Question number 9. The carbon atoms in graphite are arranged in dashed lattice and in diamond are arranged in dashed structure. Option A, hexagonal, hexagonal. Option B, hexagonal tetrahedral. Option C, tetrahedral hexagonal. Option D, tetrahedral tetrahedral. Carbon atoms in graphite are arranged in which lattice and in diamond arranged in which structure? Come on. Last two questions, this and the last one. We want good participation. Please try to answer, don't shy out. What do you think is the correct answer? I'll read the question again. Carbon atoms in graphite are arranged in dashed lattice and in diamond are arranged in dashed structure. So there is a different combination of hexagonal and tetragonal, hexagonal and tetrahedral. Try to answer, mention your answer in the chat box. I'll wait for a minute for all the students to answer. Nice, nice. People are coming up, showing up. Great. There are almost 80 to 90 people. So at least we expect some more participation, right? Students, come on. These are last two questions. I hope this explanation and practice session is helping you remember stuff and revise through your portions. Great. So many answers are here and they unanimously point at option B, hexagonal tetrahedral. Let's see if it is the correct answer. Absolutely correct. Carbon atoms in graphite are arranged in hexagonal lattice and in diamond are arranged in tetrahedral structure. Let's see quickly. So this is a representation of internal structure of a diamond and a graphite. So both diamond and graphite are allotropes of carbon. So they are all constituted of carbon atoms. See, you see the beauty of nature. Diamond is totally bright, gemstone, transparent, reflects light, total internally reflects. But graphite on the other hand is black, like charcoal, and stains paper. That's why we are using it for writing in pencils, and it's a very good conductor of electricity. So constituted of the same carbon, but in different arrangement can change the properties so drastically. So if we see the structure of diamond, here we can observe diamond is made up of these structures called tetrahedral structure, and the lattice of graphite is a multi-layered substance in which each single layer is made up of hexagonal lattices. So the answer was correct. Carbon is arranged in hexagonal form, forms a honeycomb-like structures, and many such layers are stacking with weak binding forces and strong covalent bonds between carbon atoms in the hexagonal lattice to form a loosely packed graphite. That's why graphite is very slippery and frictionless, while diamond structure is very hard because compact packing of so many carbon atoms in a small space. So a tetrahedral lattice involves 5 carbon atoms. If you look at uh, if you look at this carbon atom arrangement, so this unit is a tetrahedral unit. If you see tetrahedral, how will I explain you? Tetrahedral lattice means a three-faced pyramid. So if you have seen in movies and all, Egyptian pyramids have four faces and triangular faces which joins at the apex and a base, uh, square as a base or a rectangle as a base. So if we reduce one of the faces of the pyramids, three-faced pyramid will give is a tetrahedron structure. And at the center of the three-faced pyramid, there is also an atom. So each vertices, this atom, and this atom, and this atom. All these are the bases, four vertices of the pyramid, and these are in the 3D structure. These are pointing to the apex of the pyramid, and just direct below it, there is another center atom. So if you can see here in this structure, you see one, two, three. So one, two, three, four, 5 atoms. So here we have this tetrahedron structure. Three-faceted pyramid. One face will be this, and the other face will be this, and this. So tetrahedral lattice involves 5 atoms. Hexagonal lattice involves six carbon atoms. Because in a hexagon, we have 6 carbon atoms. Students, is it clear? Yes. Cool. Cool. Nice. Moving on to the last question. So the last question says, it's also a big statement wise question. Carefully read the following statements about capping agents used for nanomaterial synthesis. Capping agents play a very pivotal and versatile role in nanoparticle synthesis.
Statement B, nanoparticles can be functionalized and stabilized using capping agents to impart useful properties by controlling morphology, size, and protecting the surface, thereby preventing aggregation. And statement C, many surfactants have been reported to be used as capping agents for altering the desired shape and size of nanoparticles, but these are difficult to remove and do not easily degrade. So, which of these do you think is true or not true based on the options? Statement C is not true, option A. Statement B is not true. Statement A, B, C are true. Statement A and C are not true. It's a big question. Take your time. We are well ahead in our schedule. You can take your time, read this question, and I want maximum number of students to try answering this question. This is about capping agent in nanometal synthesis. Try to read the question and answer in the comment box what do you think is the correct answer. I'll wait for 1 2 minutes and check the answer. Okay, so there are few answers, more answers coming up. Good. Just try to read the statements clearly and analyze which will be the correct option, right? So more answers coming up or no? I think we should move forward. So many students have answered option C, which is the correct answer again. All A, B, C are true. That means capping agents play pivotal role and versatile role in nanoparticle synthesis, and it also helps in functionalizing and stabilizing the nanoparticle and controls the morphology size of the nanoparticle, also prevents aggregation on the surface of the nanoparticle. Many surfactants have been reported to be used as capping agents for the altering desired shape and size of the nanoparticles, but these are difficult to remove and do not easily degrade. This is also true. Surfactants are used as capping agents, but they are difficult to remove from the environment and also from the nanoparticle, and they are not very biodegradable. That's why they cause harm to the environment. Let's see what is a capping agent to refresh. Capping agents are defined as binding molecules that are used in minute quantity for synthesis of nanoparticles. If you remember the very first question that we encountered, what is a surfactant? And I told you among with the students who have answered in the chat box, high energy ball milling is the process in where we use lots of surfactants. And capping agents are also like surfactant is a type of capping agent. We will see in this slide itself. Surfactant is a type of capping agent and it acts as a binding molecule. And while some capping agents can prove as nucleation factors, some also prove as uh, non-aggregative factors. These capping agents will coat the nanomaterial which is getting reduced in size in the ball mill and then prevent them from making aggregates again.
because the whole purpose of ball milling is reducing the bulk material into smaller size. If now the smaller size nanoparticles will aggregate themselves, then then the whole energy intensive process is lost. That's why we use capping agents. Now there are some some advanced capping agents which are called biogenic capping agents, made up of biological or natural materials or naturally occurring products, which can prevent agglomeration. Or agglomeration means accumulation of different nanoparticles, sticking of sticking of many nanoparticles together, which can also help in controlling the particle size during nanomaterial synthesis. Biofunctionalism provides functional group for the attachment of drugs and other biomolecules. So while adding capping agents, we can modify the capping agents in such that they can impart many functions to the nanoparticle that is being synthesized. They can either add functional group or any other drugs or functionalize any other biomolecule. And usage of capping agents also increase the storage and stability of the resulting nanomaterials, right? And this is how a capping agent looks like in conjugation with a nanoparticle. So the big orange dot is a nanoparticle which is coated by the capping agent here, hydrophobic tail of the capping agent, and the hydrophilic head of the capping agent. So this shares a similar structure as a surfactant, because surfactant is a type of capping agent. They all have polar head group, which is hydrophilic, and a hydrophobic tail. And this coats the nanoparticle and prevents another nanoparticle to form aggregates. A capping agent is either a surfactant or polymer that is added to coat the nanoparticles. So capping agent can be a surfactant, can be a polymer. So surfactant is a type of capping agent. As the synthesized nanoparticles contain high surface energy, so they might agglomerate. In order to avoid this agglomeration, we need a capping agent. So if you remember, or if you recall, the main advantage nanoparticles provide is their high surface area to volume ratio. It means when we reduce the bulk material into such smaller size, or we nucleate a precursor material into such smaller sizes, the surface energy of the molecule increases. So all nanoparticles contain high surface energy that may cause them to agglomerate or aggregate formation. In order to avoid this, we coat them with the capping agent. Secondly, capping agent also helps to control the size of fabricated nanoparticle. So we can use many modifications in the capping agent which can help in controlling the size of fabricated nanoparticle. And to the last part where we were saying that it's not biodegradable or harmful to the environment. So you must have seen in news and in many live sightings also, there is some kind of foam coming out from the sea at some places. So the foamy sea, then kids and all love playing with the foam, but there are always government and beach guards, coast guards issue red warnings that this foam is toxic and poisonous. So all these foams are nothing but the effluents of industries which contain these capping agent. So the capping agent forms a layer of this foam and coating on the surface of water, and it's not very easily removable. There is a lot of foaming and frothing which is poisonous, which is not good for humans. So you must have seen these kind of images. At least I personally have seen. A large number of surfactant is a type of capping agent containing wastewater, are discharged into the environment, resulting in harming aquatic life, polluting the water, and endangering human health. So not only human health, The surfactants present in the water also form a layer of coating which does not allow sunlight to pass to the sea bottom and also affect aquatic life. All the fishes and turtles in the sea from the wastewater pollutant and the surfactant is very toxic. Right? So clear to everybody, do you agree with me that the answer to this question would be all ABC are true? That means capping agents are very important in nanoparticle synthesis. They control size, prevent aggregation, and provide functionalization and stabilization. And many surfactants have been reported to be difficult to remove and not degrade very easily. Is it clear to the students? Are you guys with me? You can just type yes or no. This is the last question and the last explanation that we have come across. Cool. Nice. So far, so forth. We have come to the end of this practice problem set. Now, any questions or any difficulty, I'll stop presenting my screen. Any question or any difficulty, any question you have with me. What I'll do here now is reshare my YouTube channel link. Anyways, you will be getting the uploaded video. I'll reshare the YouTube channel link again. Let me just copy it. You can visit the YouTube channel where I'm uploading the recorded sessions. So all this session will be recorded. Assignment, practice assignment week 1, week 2 are already uploaded. I'll upload the practice assignment week 3 by today. You can go there, visit them, and try to understand if you have missed some of them. And this practice assignment is just a way of your well revision and understanding of how to proceed with the assignments. So it might not be the questions that you are actually answering in the assignments, but yeah, that's it. If you have any questions, then I can take some. You can just type in the chat, or I'll allow you to like speak on the mic. If you have any questions regarding the course, or I think the lectures are pretty easy to understand. Yeah, good evening. I can take one question. My name is Dr. Gilbert. Yes, working yes. As assistant professor. Yes. In the state of Tamil Nadu, Vivekananda College of Engineering for Women. Okay. Yes, sir. So your presentation was quite informative, and today I came to know much about the importance of surfactant and the capping agent that is used and how it causes the pollution in seawater as well as the hazards that is coming up for the living organisms in the sea. Yes, thank good, you, good sir. Good to hear that. So this session is actually based on that, the interaction and the slides. So if you see for this 2 hour session, we just have 10 questions, right? But what we do is what my aim is to explain every question, and even if the answer is very simple, let's go to the root of or the background of the answer, so that we understand, we get our basics clear. Even if we encountered a modified or twisted problem or question in our life related to that, we will always be able to answer. That's what the motive of this class is. Yes, thank you, thank you. There is only one. Yes. One query, sir. Yes. Actually, this is regarding to the registration that I did for the examination. Okay. Yeah, on 15th of this month, I done the registration for exam, and I paid the fees also through online. Um, and since I am a faculty, I also registered for FDP. So 1000 plus 100. So 1100 and GST 16 rupees. So 1116 rupees I paid through online payment I did. So here the mistake what happened was, actually I'm hearing the lecture um, through my official mail ID Gilbert at the rate of bcew.ac.in.
Okay.
Mistakenly, while doing the payment for this or the registration to be done for the examination, uh, I did with my personal mail ID gilbertrosrex at gmail.com.
So
And
do
due to
you
that,
get lectures on your personal email ID?
no, that's what I hear the lecture only on my official mail ID, Gilbert. At that mail ID, I used to hear the lecture. But while registering for the examination, I mistakenly done with my personal mail ID, gilbertrosrex at gmail.com.
Okay, okay.
And
Dr.
my
Gilbert,
question is that,
yeah,
yes,
I would suggest you that
yes,
you
sir.
please write to the NPTEL and Professor Mainak Das, because
Yes, sir. I mailed him. I
yeah,
mailed sir, and still now I couldn't get any of the response from sir. Maybe sir will be busy with his commitments, but I
yeah,
couldn't
of course,
get any response.
yeah,
Can you please inform the authorities who is taking care of it and help me in this issue?
yeah, Gilbert, I understand, but see, I personally cannot on through my side actually. I am only a registered TA for this course. So what happens
Okay.
for the TA allotment? So we are from different institutes. We are all from IITs and ISers. So we are allotted a course. So we might or might not know the person, the professor personally. So what will happen is you have to constantly like query the NPTEL authorities only. What I am here to help you with is the course content and the practice problems. So I can help you in that. Good that you talk to me about your problem. And what can I say? If you
Because the last date for
yeah.
the last date for the registration to happen is on 20th, so tomorrow. So, but I have done the payment or the registration process on 15th itself. But the mistake happened was I did it with my personal mail ID, and I should have done with my official mail ID, but that went wrong, and that's what if there can anything can be changed, or can you take the problem to the higher authorities and help me, sir?
I'm sorry, Gilbert. Even I am
Mm,
the same level of clueless that you are. I
mm,
do not have much contact with the authorities. So what we are provided is with
okay.
a practice set of problems, and you just go teach the students and
Mm,
help them. Other than that, administrative areas I could not help. I'm sorry, Gilbert. If anybody else has, thank you, Gilbert. If anybody else has any doubt
okay.
regarding the coursework or the ongoing problem assignment, practice assignment, you can just ask me any course related issues or whatever you couldn't understand clearly in today's practice session. You can also post it. Otherwise, I'm going to end this session. I have shared the link of the YouTube link for all the recorded sessions in the chat box. You can just see this. You will anyway receive a mail from NPTEL sharing all the YouTube links. I will also share the presentation via the NPTEL platform. So in the YouTube link, so in the Excel sheet, you will have a YouTube link and a folder to which the presentation will be accessible. So do not worry and keep following the lecture slides and solving your assignments. Good luck for your exams, and I'm happy to help anytime. See you on next Monday with practice problem set 4. Thank you. Bye bye.